Hello everyone. Welcome to the 12th session of our 3D Thursday webinar series. It's great to have you with us as we dive into the world of additive manufacturing. Today's topic is how software unlocks additive manufacturing for jewelry production. We look at how the right software stack combination, advanced computational methods with real manufacturing expertise, enables additive to deliver more than just printable parts. So, using jewelry as a focused case study, we'll explore how to apply lightweighting strategies without sacrificing strength and aesthetics, and how to generate build ready designs with highly intricate features that are difficult or impossible using conventional technique. So, how to improve casting outcomes by leveraging AM informed geometries and process aware design. So, while our examples come from jewelry, the principle transfers directly to other precision driven domains as well, where design, freedom, efficiency, and repeatability are critical. By end of this session, we expect a practical understanding of how software workflows such as lattice generation, topology optimization, build preparation, simulation can de-risk the production, shorten lead times, and elevate part quality. So we are excited to get started, and we want to make this session interactive. We always welcome questions. A dedicated Q&A session will follow the presentation, but questions can be submitted anytime during the entire time in the chat box. Similar questions may be grouped so more voices are heard. We'll cover as many as possible as the time allows. So please jump in with your thoughts and questions. So with this, please note that this webinar is being recorded. By participating, you consent to its use and share for educational purpose. So I'm excited to introduce our speakers for the day. First, Mr. Rohidas Alkunte, Senior Advisor, Samsung Tech Private Limited. He holds a BE in Mechanical Engineering from Mumbai University and brings about 24 plus years of experience in jewelry manufacturing, casting, and process engineering, with prior roles at Unidesign Jewelry, Elegant Collections, Intergold, and other leading organizations. Joining him is Dr. Jeet Desai, CTO of Samsung Tech Private Limited. He earned a BE in Mechanical Engineering from BITS Pilani and a PhD in Applied Mathematics from École Polytechnique Paris, with industry funding from Airbus, Renault, Safran, and ESI. His expertise spans computational geometry, high performance computing, and topology optimization. Please join me in welcoming Mr. Rohidas and Dr. Jeet as we lead us through today's presentation. Over to you.
Uh, Thank you, Manish, for your kind introduction. Right. So I'll first talk a bit about, like, just give a brief background of our company so that everybody has a context of what we are currently working on. And then I'll let Mr. Rohidas speak about AM in jewelry. Second. So our company, Samisan, makes software. We are in the jewelry industry, so we make the software for CAD designing, for CAM, for casting, everything. And we sell licenses in United States, Europe, Middle East, etc. Then we also make build preparation software for additive manufacturing, where we like our software does everything from mesh repair, automatic supports, nesting, and other features, which are very common. Then we also have a software for 3D inspection. Like, let's say you have a 3D scan and you want to compare it with a CAD, our software does it automatically. And last but not the least, we also do consulting. So we are currently doing consulting for this, for steel industry, wherein we customize, like we develop parts which are which can improve production in steel manufacturing. Right. So now I'll let Mr. Rohidas ji explain the evolution of AM in jewelry over decades, and it would be very exciting. So, yeah.
Thank you, Jeet. Thank you for the lovely introduction and putting the background in context. So I hope everybody is aware of jewelry manufacturing is a separate industry in India. And the interesting part is it is the second most, I mean, after software, it is the second most foreign revenue earner for the country. I mean, after the software, this industry stands in second in terms of exports valuation. So, though I am from background, I started my journey with jewelry manufacturing company in 2001. I mean, it was in quite coincident because I even happened to do CAD CAM course, and I think that time it was software like ideas. This software was basically, I mean, used for surface modeling. That time, this was quite popular in surface modeling. In 2001, I was discussing about, and one of the jewelry companies has taken the bold step to introduce this surface modeling software in making jewelry. And we are the first, I think, 10, 15 people who have been hired um, because of our engineering background or in education, and plus some exposure to the CAD CAM industry. And there the challenge was to see how can we make jewelry manufacturing, the masters basically. Those days, the master used to be made. I mean, I hope everyone understands the master. Master is a main master which they cut the mold out of it and then they produce multiple number of pieces. So this is how jewelry manufacturing works. So those masters used to be prepared with the hand, and one master used to take almost 3 weeks at least. And so this company Intergold decided to introduce CAD CAM technology and make masters. And trust me, we are the first batch of people who got an opportunity to see the 3D printing, that is SLA, 3D printing machine designed by and developed by 3D System Germany. So we were the first company to import the 3D system machine in India in 2001. So the export order was placed in 2000, and the waiting period was almost 8 to 9 months, and the installation commissioning was around 2 months. So this is how the journey began. The Viper Si2 with initially it was a transparent resin, and I think after 6 months they introduced amethyst resin, and the claim was this can be directly castable because to converting that. So first we used to make a CAD. That CAD used to be 3D printed, and then we used to make a master out of it, then inject molten wax, take out the casting. You can see the can you click the image? Third. You can see this is a rubber mold, and you can see the green color wax output. So first is the a little here it is showing a little bit black color, but it's an amethyst resin output. Then the mold is cut in the rubber form, silicon rubber. Then they pull wax out of it. This wax is sent for silver casting. So this silver casting is finished and kept as a master model. So whenever you get an order, they inject the wax piece through the rubber mold and produce multiple pieces. So the requirement is to produce similar multiple pieces, or maybe in 1,000 or 500, depending on the orders, similar multiple pieces with the same mold. So this is how they used to do patterning. So, but this technology was very much limited to, I mean, very few companies in SIEPs. SIEPs, just for your introduction, I'll just give you the background. What is SIEPs? SIEPs is an SEZ located in Andheri, East Mumbai. So in this zone, there are almost 70 to 80 jewelry manufacturing companies, and these companies are very well advanced in their manufacturing techniques compared to rest of the country. So if you see any diamond jewelry manufacturing company, you want to see the best top-notch technology implementation, and I mean they have adapted to the technology. You can see any companies in SIPs. So this is how the journey began. So additive manufacturing was entered into jewelry, I would say in 2001 or even around 2000, and couple of machines were bought which were printing wax. So preparing that mold was eliminated. and that wax was directly casted into silver. Able to explain it properly any because this is totally a different jewelry manufacturing sector. So feel free to ask. I mean, it can be like given. I don't mind giving any explanation in the middle of the presentation because understanding this process will definitely help us to take something from this presentation. So moving forward in 2019, the widespread happened because till 2009, 10, and 11, the cost of this technology was very high. I think in 2001, that time it was costing us 1.25 crore rupees, and for that in 2001, the cost of 1.25 crore is very high compared to the ROIs and other investment. But the company was very much inclined towards automating this skill-based work to computer CAD CAM and AM technology. So eventually, after 2020, 12 and 13, the DLP printers have changed the game. Because of the cost, they have become so popular. The accuracy was slightly different, but jewelry was never meant to get like accuracy. Their main focus was to get the output and the aesthetic. So 18, 19 was like almost every small manufacturer was having a AM machine and a software to produce a CAD and to print a CAM. So now, almost if you see, this industry is very well, I mean, recognized. Like you see, the best of the best machine they have like bought from countries like Italy, Switzerland, Germany, and they are like in the process of implementing all these technologies. So nowadays, Chinese machines are also very popular. So and they are cheaper. So this LCD, LED, LCD printers have changed the game because of the cost. So we'll go to the next slide. So what are the advantages which are helping jewelry to adopt AM? It is a low volume, high value. I mean, jewelry patterns initially in those days, back 20, 15, 20 years, one pattern used to get multiple number of pieces, like say 2000, 3000. But nowadays the designs have increased. So one design may hardly get a piece of 20 pieces or 30 pieces order. So this AM is a key where it can be, the total turnaround time becomes shorter. That is what my next point is. Low turnaround time for master, or even nowadays 3D wax printer are allowing us to take it directly for gold casting and minimizing the precious metal wastage. So initially the carving was done. The process was like carving out of a metal box. Now you are just printing what is needed through CAD and CAM, and then that is you have been cast with the lost wax method. You can see one bracelet which has been 3D printed, so assembly process is totally eliminated. Bracelet image. Yeah. So this entire wax bracelet was 3D printed on a 3D systems wax printer, and the diamonds are directly set into the wax. So you will get after casting, you will get a direct gold bracelet, or like pre-assembled. So this helps us to reduce a lot of skill-based work. So this is how this industry has adapted the AM to reduce its dependency on skill and improve the turnaround time. Moving to the next slide. So in today's world, 95% of the casted jewelry are manufactured using AM. So you can see the amount of penetration AM has got in this last 10 years in the jewelry industry, where people were dependent on like labor skills, and they were totally more inclined now to shift their skill based work to AM technology and additive manufacturing. So here is a bit small representation of journey, how this jewelry is being made. You can see the first image. That is a simple sketch. Yeah, this is a sketch. Now that sketch is converted into a CAD file. Then the same CAD file is given to a printer, 3D printer. Any wax printer can give you this output. And this has been casted, and all the jewelry diamonds are being set and finished. So this is a transition of a sketch concept to a final jewelry. So this is how, so this you started, like people started pre-visualizing, like they can get an estimate of volume in the CAD file, they can predict the weight, they can decide what shape of stone can be set and what size of stone can be set. So these all predictions started helping them to give quotation in advance. And also if you see the export markets, all these jewelries are they are price based. Like when you sell a jewelry to the supplier or a wholesaler, it has been like the price is fixed, like $400 or $499, $599. So these price points are fixed, and then they have to work backward calculation how they can achieve the required gold weight and diamond weight. So here the AM and the softwares are like very useful for a jewelry manufacturer to plan his sample. Now the next level is helping achieve the shapes, because in jewelry the shapes are very critical. So in old days, if you see the left and right earring, they are reflect of each other. So with manually, people used to take more time to match the left right and earring and right earring master. But now with the softwares, just one click and you can just transfer the you can 3D print those masters, and any complex design you can do. So this complexity and the skill has totally been eliminated. The accuracy was very high, the comparison was good, and the end customers also started liking more AM printed and software based products. So this is how these penetration of um, AM was very evident. You can see, and the utilities now, initial days only qualified engineers used to operate these softwares and machines, but now it has become so popular that anybody, if you ask jewelry, they want to shift to CAD CAM and AM. Like for them it's like CAD and CAM, so they call it a CAM manufacturing machine or CAD software. So their trend is very high towards getting knowledge of this technology and working on the software. So these are, I mean, say two technologies which is very widely used and adapted very well. One, if you can see on the left, multi-jet printer. Here the wax is the output. Second is DLP, SLA or LCD. These are the machines which have changed the total industry. And now the industry is directly, their approach is to print everything in direct gold. So people are exploring if it is possible to get the 3D printed. Now the challenge is to get a correct surface. So if anybody can give this surface in say 2 or 3 micron array value, then I think they are the like there no one can stop them being a billionaire in this industry. So this is an opportunity you guys can think of, and if somebody has a solution, please think of making a machine. So in metal printing also there is LPBF and binder jet technology. So you can see the binder jet, you can see the animal shape. It is the assembly is already done in the CAD, and the assembled part was printed. So this is just to demonstrate these pieces. We have taken the images from the pioneers like Legor and other people. So moving to the next slide. So challenges are there during while these technology has been adopted. One is your handling of fragile pieces, gross loss in gold jewelry, because now today's gold rate is almost, it has touched 1 lakh rupees per 10 grams. So the more rough surface, the more you need to finish and the more gross losses are there. Though they have a recovery system, but still um, they need to minimize those losses. Cleaning supports material elimination after removing from AM machines are still a challenge. You can see the casting defects because anything which is printed today is been casted in gold. So the lost wax through lost wax casting method, and the casting defects are like one of the biggest challenge everyone is facing nowadays in the industry. So taking forward, we are like my interest of area of interest is to focus on more on this particular domain of casting and how we can first eliminate the total manual work involved in the casting, and that's how we have like working on some of the softwares and automation, how we can eliminate the dependency of labor in this particular area. Uh, so these are the very common defect in this particular segment. You can see the shrinkage porosity, gaseous porosity, unfilled castings, dents. So these are at a very the industry is still at a very nascent stage. Even categorizing this problem and identifying them, giving them a standard terminology, making standards in the organization to identify the problems. Even these steps are taken by very few industries, especially like two or three companies in SIPs, because know-how of this particular process is very limited to few people, and acceptance of learning new things in this particular domain is very I mean a challenge. So yield is one of the challenge, like how much gold I'm investing and what amount of pieces I'm getting out of that gold tree. That is an yield which is very limited to 25 to 30%. And even that area we are focusing with some automated solutions. And AM is playing a critical role in this particular segment. So I'll just explain you this in my next slide. Yeah, so casting, these are the few challenges we are trying to address with the simple gating. And instead of putting a manual gating, we are applying, our approach is to print tree, a casting tree directly in with AM. So this is totally eliminating the work of manual involvement, designing the gate screws, and analyzing the part for getting a good casting. So this is helping. This is where the softwares are helping us to design the gateways, and the AM is helping us to print it as per the accurate dimensional requirement.
Yeah, please.
Yeah. So I was just saying that. So I've worked on topology optimization applied to like diverse physics like contact mechanics, plasticity, elastoacoustics, etc. And like these are just a few of my publications. And I belong to the Euler lineage, meaning that Leonard Euler, you must have heard about him. Yeah, uh, like a renowned mathematician. Like his PhD student was Joseph Lagrange, and then his student was Denis Poisson, and then that lineage is still in Paris in École Polytechnique, and I'm fortunate to belong to that lineage. So like my supervisor is Grégoire Allaire. He's one of the most renowned mathematicians in applied math, like in the world, and right a bit about my PhD. So I had worked on topology optimization using state-of-the-art method. So you would have heard a lot about topology optimization, a lot of like there's a lot of noise around it, like it can reduce weight, it can revolutionize parts, assemblies, etc. But so far we've seen that nobody is really using it. And there's a reason behind it. Because these parts that topology optimization give are too complex. Too complex, they are not time tested, they do not account for complex fatigue load like fatigue phenomena, and the method generally results in very complex topologies like very thin features, very thin bars, So here, what I'd worked on was how can we minimize that? Like what technique we should do this optimization so that we have a simpler geometry. So here you'd see a topology optimization for bridge, three columns, chair, and you'd see the evolution of shapes uh, in time. So basically, the algorithm is trying to improve the design step by step, and once it converges, the design does not change. Right. So the bridge, for example, hasn't converged yet. And you see that towards convergence, we get a bridge that actually resembles an I-beam. So like the corners of this beam, of this bridge, they resemble an I-beam. So this is very intuitive, and this is what an engineer would expect. Right. So yeah, so this result has been published in Journal of Computational Physics. And yeah, so like Manishi mentioned that these companies funded my PhD. Right. So now I'll move towards design for jewelry using additive manufacturing. So first, before talking about design, I should talk a bit about how designs are made. So in engineering, all of us knows like we've all used AutoCAD or SolidWorks. We start with a main like the main piece, and then we make cutouts, we do extrusions, and we make sketches on the part and we carry on. In jewelry, it's not that way. In jewelry, every feature is designed separately and then assembled. So for example, in this ring, we would make this the shank of the ring separately, the top portion separately, this rail separately, and then assemble all of it. So in jewelry, right. So majority of this design is made on a software called Rhino, and it is, like I mentioned, composed of several features designed one at a time. And every feature we can do scooping or hollowing. So for example, in this ring, you see that this shank has been scooped. So there's a cutout. Why do we make that cutout? So that we reduce the weight of the ring. So from the outside, it appears that, oh, the ring is very heavy, it's bulky, but from the inside, it's hollow. Now, given that gold has become so expensive, we would want to make a design that is as light as possible. So the question is, uh, what can we do? We have a casting constraint on the design. So we know that we can cast only up to, let's say, zero point 0.4 or 0.35 mm. So the question is, have we ensured this thickness in the design? So does the design have the same thickness everywhere? So so far in the industry, there is no way to visualize the thickness of an entire design at once. Like there's really no way to do that. As in, you have a design, like trust me, like this in engineering, our files are not that heavy. Like our files are maybe 100 megabytes. But in jewelry, even a simple ring is more than 100 megabytes. Like it can be in gigabytes. So there, visualizing the thickness is very difficult. So we've developed a tool to visualize the thickness instantly. So this ring, we just load it on our software and we can see the thicknesses instantly. So here there's a color map, and it says that wherever we have a lot of thickness, more than 2 mm, it becomes blue. And a few places you see it's green, a few places it's yellow. It means that it is a zero point 0.6 or let's say more than 1 mm. So it means that the thickness is not uniform. So we are basically wasting a lot of metal. And this is the case with 99% of the jewelry that you are buying or you're seeing around you. So right. So as I mentioned, the thickness is not uniform. So now the big question that we can ask is, can we enforce the same thickness everywhere? If we can, it's a game changer, because then a 9-gram ring will become like 7-gram ring, or we can expect a lot of weight reduction. So yeah, so there's a small video on that. So the software, you see that the one that we've developed, it automatically identifies the inner surfaces, and then it reduces, like it removes metal from the inside, so that we can ensure a constant thickness. Right, so it's doing that. So this is happening all real time. Right. And here you see that we've reduced around 2 grams, 2.4 grams in the ring. Uh, so the aesthetics is the same, as in before and after it would look the same from the outside, but from the inside we have reduced metal. And so this is the result after that automatic, we call it scoop, like automatic scooping. So here you see that it's red everywhere. So red means that, like on the color scale, it's less than 0.35. So we've ensured that casting thickness almost everywhere, like on the top portion where the stone is going to sit, on the shank, everywhere we have the same thickness. So we've reduced a lot of weight. We've reduced 27% of the weight, and we've maintained the design. And there's a bonus. This helps in casting. How? Because when we are casting, there is an inlet. This inlet has to be at the thickest portion of the design. If you have multiple thick portions in the design, you need multiple screw inlets because the thick portions are going to cool in the end, like the last. So when in casting, when we've poured the metal and solidification happens, the thinnest portions cool first, and then the thickest portions cool. If the thickest portion do not have feed, like the thickest portion are like shrinking, the thin portions have pulled all the metal, the thick portions would end up having cracks in them. And these cracks are called shrinkage porosity. And this is a very, very big problem. Like this problem, like, okay, there are ways to resolve it. We'll like hammer it, or we'll do a lot of polishing. There are many ways, as Rohidas ji can talk about. But why do we want to do all of that? If we've made the right design, we don't have to do all of that polishing, right? So scooping would help in avoiding that because we mentioned the same thickness everywhere. The chances of shrinkage porosity have been minimized. Right. So this is one more example of how scooping helps. So this design, as you see on the left, this had been made by one of our customers, and this design on the right is what our software is able to do. Like from the outside, you'll see that we've maintained the same aesthetics, but from the inside, you see that like there is this lion face. There has been additional scooping, so like the hair of the lion are more as in sharply defined. There's an azure cut. Okay, I'll talk about this in the next slide. And the inner surface scooping. So here we've reduced 35% weight. So on an average, we've seen that we're able to reduce anywhere from 15 to 20%. This is the average. So we can even do more than 20% weight reduction. And there's one more thing that I would definitely like to talk about and then relate it to the engineering domain, and that is the hexagonal cutouts. So whenever jewelry is made, on the backside of the stone, initially, like 20 years back, they used to have solid metal. Like on the backside of the stone, there used to be solid, like there used to be gold. Later on, they realized that, oh, nobody's looking at that. Why do we have gold there? So then a few intelligent people said, okay, we need to remove that gold. Okay, so they made holes. They made cylindrical holes behind the diamonds because nobody's going to see that. Then, like 5 to 6 years back, they optimized it further, saying that if we have a stone, we can cut it. We can make a bigger cutout from the backside of the stone, so that we can reduce metal even further. And not only that, we'll by reducing metal from the backside of the stone, we'll enhance the brilliance of the stone, as in the stone, because there is no metal from the backside, it will appear more brilliant. So it will improve the shine of the stone. So this hexagonal cutout, people usually design it like manually, like they make that design on CAD software. It is very tedious, like it's very tedious. Like it would take hours to make a cutout like this on this, the one that you see on the screen. But we've been able to automate it. Like it would take like less than a minute to do using our automated solution. And right. And here, one more thing that you see is that the hexagonal cutout is oriented along the surface. So like the hexagon aligns with the surface. It's not the hexagon that we generally make on a CAD software, like just a hexagon cutter and then we just extrude it. It's not that. Right. So now we can extend this to engineering. So here, for example, there is a piece on the left. You see that it's very bulky, a lot of weight. If we were to manufacture this using AM, there's a lot of scope. We can lightweight it. So here, this is a lightweight piece on the right, wherein we have done scooping, as in you see that all the surfaces, a thin wall has been preserved around those surfaces, and there's a hexagonal lattice around it. So the hexagonal lattice will ensure that there is strength. Like there is no diamond over here, so we just like here we do it for strength, and the thickness has been preserved. Okay, so now some of you might think, oh, I can make this on CAD software also. The answer is yeah, you can make it on CAD software, but how long will it take? Here, it would take like less than a minute. Like you just click on the surfaces and we've automated it. So then the point is that you can spend more time on designing and less time on, like tedious, laborious work, which does not add a lot of value. And then taking this idea further of scooping, we've made a solution wherein, so this is a case of a spinal implant. This is normally solid, like there is no lattice inside, like it's all solid, which makes it very heavy and it's made via additive manufacturing. Here we've preserved a few surfaces and the rest has been, instead of a hexagonal lattice, we've added gyroid lattice. So, right, so we are able to add any kind of lattice like rhomboidal, gyroid or Schwartz lattice. And software plays a very important role. When we add lattice, this is not even possible on a CAD software. Like CAD software cannot make gyroid lattices or rhomboid lattices. This is only possible by very specialized software. Right. And I'll just talk a bit more about one more application of this. It's in the steel industry. In steel industry, there is we are working with one of our clients. So uh, uh, I'll talk very briefly about the application. So we need a cooling device wherein there is a cooling jacket and a tube inside it. Uh, so this, like generally there's an assembly which has more than 100 parts and it weighs 140 kilos plus. The tube on the right you see is made of copper and the cooling jacket is of course made of MS. So this we've redesigned it using the same approach that I talked about, scooping plus lattice infill. So here we've replaced that entire assembly by a single part, and it's 3D printed in copper, like 400 mm height, completely 3D printed. And this is how the inside would look like. It's a very complex design, and you see that the lattice is oriented along the surface. So this is what I was talking about. Like we are able to make lattices which are oriented or aligned along the surface. This, if you were to try making on CAD software, it would be a nightmare. And right, so this design was possible only because of AM. Like because AM allows to print us like print anything. We can really make any design and uh, make very complex design and reduce the weight, the assembly, etc. And yeah, so because we are working with our client, so we'll not share a lot of information on this. But if anybody of you is interested, we can definitely have a detailed session later on. So I would like to conclude our talk by 3 points. Number one, we've solved the casting problem wherein like we saw, there are a lot of defects. Uh, we are solving it using an automated sprue, and this automated sprue would not have been possible without additive manufacturing. Like we discussed that wax, like we'll print that part in wax, and then manually you cannot make it. Like manually, if you were to try soldering it, it would not work. It's too complicated. And of course, when we make the sprue automatically, it has been made as per some simulation and empirical rules. So the casting failure is minimized. So the rework, as in when you saw those shrinkage porosity like Rohidas ji had shown before, whenever that happens, the piece has to be reworked. That we are able to minimize. Then lightweighting. So by scooping, so here this is very important to note, which is generally like I've worked with a lot of people, and all of them would say, "Oh, AM is too expensive. AM is just not affordable. I don't know why how AM would even scale." The problem is people are just trying to print an existing design that they made via casting. The point is, why are you doing that? Like, why are we using AM to print existing designs? No, that is not how we'll exploit AM. If we want to exploit AM, we have to first redesign the part. We have to simplify an assembly. Like the power, like the advantage of AM is we don't need assembly. We can replace entire assemblies by a single part and make it lightweight. So that is like redesigning, re-engineering would really help to exploit AM. And of course, like so that is one side, and the other side is lightweighting designs using scooping and lattice. Would if you were to make like if you were to cast it, like let's say we've kept casting constraints in mind, then we can also improve casting because like in jewelry, I discussed that if you eliminate thick regions like thin regions, then the shrinkage porosity can be minimized. And the shrinkage porosity is also very common in metal casting, as in like in engineering applications. So there, this would reduce the number of runners, the size of inlets, etc. And yeah, you need the right software and the right engineering know-how. And this know-how, like this automation of sprue and design, we've already applied to jewelry. We've demonstrated it successfully. We have customers who are using it every day. And we are very confident that we can apply this to other industries as well. Like in the previous slide, I talked about an application in the steel industry, but there's a definite application in the automotive, aerospace, or medical. And it would use the same principles, like you give us the part, we do simulation, and then we optimize the design, and then we use AM. And jewelry, like jewelry for us is like a test bed. As in jewelry, the part is not a functional part. Like the function of a jewelry is what it just has to like exist. It will not be subjected to a lot of mechanical forces. But if AM is helping us get results over there, then for sure the same methodology can help us in other industrial applications. So yeah. Uh, thank you everyone for your attention. And I would like to conclude our presentation.